Hi, this is the movie that goes with the first part of lesson 7. We're going to do a few different sections in chapter 11, and then we're going to jump to chapter 17 for combined stresses. The first topic is stress concentrations. So far, when we talked about an axially loaded part, we always talked about the stress as being what we call the average stress, where we take the stress, we take the load that's applied to the part, and we divide it by the cross section. And what that gives us is a uniformly distributed stress across the cross section. That's what this picture here tries to display. But experimentally, we know that if there is the presence of a discontinuity, in this case a hole in the part, that hole being a stress razor, it has an impact on the stress distribution. Okay, so what we're seeing here is we have a maximum stress right at the hole, and it tapers off to a minimum stress. Now, the maximum stress is greater than the average stress. Like right here, we're talking about the average stress. We talk about a net here, that's the net area, which would essentially be the area of the cross section of the bar minus the area of the hole. And we know that the maximum stress is greater than this average stress, and we know that the minimum stress is actually less than the average stress. So we need to account for this maximum stress using stress concentrations. And we also talk about having notches in the bar here, and then this is what the stress distribution would look like. Or if we had a fillet radius here, where the section of the bar necked down, we would have this type of stress distribution. It's important to recognize that these discontinuities change your distribution of stress, and as a designer, you need to be aware of this. Okay, so this gets us to the point of a stress concentration factor, where the maximum stress is going to be this K factor times the pressure divided by the net area. The concentration factor we're going to read off of a chart. P is the axial load, and then net area. That is the cross-sectional area in the plane of the reduced cross-section. Then we have figure 11.14, which has a chart. The chart has 3 lines on it. The K factor is read off the y-axis. The input to the chart would be this R over D, in which case here you have a 2R over D. There's different ways of getting this based the R over D. So each one of these has an R over D. So what you have to do is calculate the R over D. You find that on the x-axis, and then you come up until you intersect what type of stress riser this is. The first line here is for a circular hole. The second line here is for semicircular grooves, and this line here is for fillets. You take the R over D, you intersect it to the correct line, and then you read the K factor off of the y-axis. I'll cover example 15 in the examples movies. So that was the first item, was stress concentrations. The next item is stresses on an inclined plane. The discussion here sets up where we're going with the combined normal and shear stresses. So what we have here is we have just a loaded bar. Okay, it's axially loaded, and everything's in equilibrium. We know that the maximum normal stress is developed in the plane perpendicular to the load direction. This is what we've always done before. We would have this plane AB, we would calculate the area. The stress based on the load here is the force divided by this area in the load plane. But if we were to look at this a little bit differently, if we were to look at an infinitesimal stress element in the middle of this part, and we were to rotate the orientation of that stress element by this angle theta, what we're going to find out is that it's not just normal stresses, that we also have shear stresses that exist on these planes other than the normal AV plane. Okay, so what we're going to have here is we're going to have a combination of tensile and shear stresses at plane C and D. To do that, we're going to derive these formulas here. There's really, in this section, there's only two formulas. This would be what the normal stress is at that inclined plane, and then this formula here is what the shear stresses are at that inclined plane. We go through some derivations of this in your textbook. I don't want you to freak out too much about this one right here, but this was one of those double angle identities. If you had sine theta times cosine theta, if you look this up in Google, you could get to 2 sine 2 theta equals sine theta times cosine theta. It's just a double, what they call it, double angle identity. So we really only have two equations, but the point here is that shear stresses and normal stresses exist, just based on this normal stress. So far when we're talking about this, we just have normal stresses based on this bar being loaded, and we were just considering the plane AB. So now we're expanding our definitions. We're looking a little bit deeper into this, and we know everything in this bar is in equilibrium. Okay, so what we're doing is we're changing the analysis to look at an inclined plane, CD. What happens along this inclined plane? Okay, so we have our two equations for this section. These are the only two equations for this section. Problems in this section aren't that hard, but I'm talking about this to introduce the concept of when you have normal stresses, that if you looked at it at an inclined plane, you're actually having shear stresses and normal stresses. Okay, so if we look at the shear stress formula, we have this term sine 2 theta. This shear stress equation is going to give you a maximum shear stress when sine 2 theta equals 1. Okay, so that happens to be when theta equals 45 degrees. Therefore, the maximum shear state exists at a plane 45 degrees to the load direction. Okay, so maximum shear stress is going to occur at a plane 45 degrees to the load direction. Okay, and then we're going to go over examples 11, 17 in the examples problem. Next, I want to talk about shear stresses in mutually perpendicular planes, but I'm going to save that for the next movie.